All right, folks, so we've been working on differential equations, and the classic example of a differential equation is talking about the rate of change of an object cooling or heating up. And the idea is that the rate of change of the temperature of an object is proportional to what the object's temperature is minus the surrounding medium, so the surrounding environment. And so this means that when there's a big gap between the temperature of your thing and the environment, it's going to change temperatures very quickly. And when they're very close together, it's still going to change temperatures, but it's just not changing temperatures as quickly. And so what we can do is separate variables here and get Tt divided by T minus T naught is K dt. Remember that the letters K and T naught are constants, so they're not actually variables. So when I integrate, I only have two variables, big T and little t. The integral of the left side becomes the natural log of T minus T naught, and the integral of the right side becomes K little t plus C. Then we do our exponentiation of both sides, and we get absolute value of T minus T naught equals e to the kt times C. I did the trick there where I thought of e to the kt plus c as two things multiplied together, e to the kt times e to the c. E to the c is just an arbitrary constant, so I might as well write it as c. In fact, some people like to do the same thing with this e to the kt. I don't believe I showed you this in class yet, but you can write that as c equals c and then k to the t. Because e to the k is just a constant anyway, and e to the kt is just e to the k raised to the t power. So you can do it that way, whatever makes you happier. To deal with the absolute value, you have to do a plus or minus. So positive or negative c times k to the t, and then add t naught. And I want you to think about what this is saying. This is saying that you have either a positive or a negative exponential curve, and you have here a t naught that you're adding to it. Well, exponential curves either look like this, or they look like this, or if they are multiplied by a negative number, then you have them looking like this, or looking like that. Out of those four different possibilities, there's really only two that are going to happen, because over time, we know that the object will approach the temperature of the environment that it's around. So we're either going to see a curve that looks like this. That's not steep enough. Exponential curves are pretty darn steep. So it's going to be a curve where over time it's coming steeply down like this and then flattening out, or it's coming steeply up like this and flattening out. And the equation of that horizontal asymptote is whatever the surrounding medium is. Okay? So in a particular example, the textbook told us some things. So let's use those things to try to solve for our three constants. Here's a big picture idea. Whenever you have things you need to solve for, you need at least one clue per piece of information. So I have a T naught, I have a C, and I have a K. I need to have three pieces of information. So in the textbook's example, it says the initial temperature is 100, then it's 80, and then it's 65. So when it's 100, that's at the beginning of time. All right, so I plug in 0. And then k to the 0 is equal to 1. So I just get 100 equals t plus c. And we can really just do plus here, because plus c or minus c, it just you're going to have a positive c or a negative c. You can combine them into just one thing. Just keep it plus to make it simple. Okay, in 10 minutes it reaches 80 degrees. So 80 is going to be, I should have put T naught there. So 80 is going to be T naught plus, and in this equation here, you can either solve for T naught or you can solve for C. Is one easier than the other? I don't really think one is easier than the other. I'm just going to solve for T naught. So it's just 100 minus C is T naught. And so then I can actually throw that into my second equation. So we have 100 minus C plus C times K to the, it took 10 minutes allegedly to cool down to 80 degrees. Okay, we can use that to solve for the letter C or the letter K. I'm going to solve for the letter C, so I'll subtract 100. So I have negative 20, and I'll factor out a C times negative 1 plus K to the 10th. And so then now I know that C is negative 20 over negative 1 plus K to the 10th. And then my last piece of information they gave us is that it's 65 degrees after another 10 minutes. Just make sure you're keeping a track that that's another 10 minutes. So we're actually going to plug in, we're going to plug in 20. And I'm going to not write the letter C. I'm going to write what I just solved for in terms of, I solved for C in terms of K. So I'm subtracting negative 20 over negative 1 plus K to the 10th. So remember, I'm going back up to this equation right here, and I'm the equation right above it, I'm plugging in 20 and 65. Okay, so that's T naught, and then C is given right here. And we have K raised to the 20. Okay, great. So after all of that, we can solve, allegedly, for what we need to solve for. Okay. If I subtract 100, I get negative 35. Both of these terms have the negative 20 over negative 1 plus K to the 10th in common. The first term had it with a negative 1. The second term had it with a K plus, or K to the 20th power. All right, we're going to create some space over here. We're getting somewhere. Just a few nasty steps of algebra, and then we're done. At this point, it's no longer the calculus. All right, so let's do this. I'm going to multiply. I want to get rid of something here. I'm going to multiply both sides by negative 1 plus K to the 10th. So that's going to be positive 35 minus 35K to the 10th equals, and I'm going to distribute the negative 20. So I did multiplied by negative 1 plus K to the 10th, and I'm going to distribute the negative 20. So that equals 20 minus 20K to the 10th. Or, no, K to the 20th over there. Let's get everything on the left side so it's equal to 0. So we have 20K to the 20th minus 35K to the 10th plus 15. So I subtracted 20 from the 35. Let's make those smaller. Those are all divisible by 5. So I have 4K to the 20th minus 7K plus 3. 7K to the 10. Can I even factor that? That's a good question. Let's see. I think I can. It's 4 times 1. Yeah, okay. So if I set this up to be 4K to the 10th minus 3 and K to the 10th minus 1. See if that works out. You could also have used the quadratic formula. You just would have been solving for it in terms of k to the 10th. But I think this works out because the 3 times 1 is 3, and I have 4 times 1 and 3 times 1. Yeah, that makes 7. So now I have two possibilities. I have this one, which gives me k equals plus or minus 1, and this one, which gives me k equals plus or minus the 10th root of 3/4. Okay, plus or minus 1 doesn't work. I don't know if you can see why. If you've got your head above water, I'm not sure, but we can look back. We know that c, remember, we're trying to find our constants. C was defined in terms of k. And if I look at k equals 1, well, then this is equal to 1, and negative 1 plus 1 is 0. So that is no bueno. The other k values end up working out the same, pretty much the same way, but the negative value would make it bounce between a positive and a negative, because if you have a negative base on your exponent, it switches between positive and negative, positive and negative. That's not how things cool down. So we're going to keep just positive 10th root of 3/4. From here, it's not so bad to find the c value, which is just negative 20 over 1, negative 1 plus 3/4, because we had the 10th power and the 10th root. So that's negative 20 over negative 1/4, which is 80. And once we know the the c value, the t naught value is easier to find too. It's just 100 minus c. So 100 minus 80 is 20. So we know that over time, our object's going to cool down and approach 20. That's the temperature of the laboratory. And if we used our solution, we could predict the last question in the textbook, what the temperature is after another 10 minutes has elapsed, which I think is 30 total minutes. So we say that's 20 plus or minus 80 times the 10th root of 3/4 raised to the 30th, which is just another 3/4 applied to the previous answer. If you type all that in, let's see, so 20 plus 80 times, it's going to be 3/4 to the third power, gives me 53.75 degrees. Notice that what's really happening is that in the first 10 minutes, it is 3/4 closer. It was 80 away from 20, then it's 60 away from 20. So that's a 25, it's a quarter closer, or 3/4 of the distance. Then it's from 60 away to being only 45 away, that's another 3/4. And then from 45 away, now it's 33.75 away, it's 3/4 closer. So thanks for watching. There's other ways to solve for these constants. This was just the way that this video sort of unfolded, but there may have been a more elegant way to simplify it as we went along. So ask questions, let me know what I can help with.